If you look at the data specifically, you're going to find learning, but for that, there's several requirements. Has to be the same site, has to be the same constructor, has to be at least 2 years of gap between one construction to the next, have to be constant labor laws, have to be constant regulatory. And when you add these five, you only get like 4 or 5 examples in the world. And you from those examples, then you can see learning. So it's gonna basically be a challenge in terms of standardization.
A warm welcome back to Decouple. Today I'm joined by Professor Koroush Shirvan. Professor Shirvan is a nuclear engineering prof at MIT. From what I can gather from the bio, specializing in development assessment of advanced nuclear reactor technology, innovations in nuclear fuels, reactor design. But Koroush, really, it seems like your fingerprints are everywhere these days. I know you do a lot of consulting. You've been helping crunch numbers for a variety of major reports that have come out recently in terms of the DOE liftoff and I think the TVA IRP. So what better man to get in the podcast to assess some of the, ever more frequently kind of breaking news and updates, which are rapidly sort of shifting the dynamics of where we're at in this exciting, I hesitate to say, nuclear renaissance. So Koroush, real pleasure to have you on Decouple. Thank you for making the time.
Yeah, no, thank you for having me, Chris. Look forward to this discussion.
Okay, and feel free to flush out that illustrious introduction a little bit if I didn't do you justice in some way, shape, or form, or to clarify anything that I was saying.
No, you covered very well. I am at MIT, so whatever I do is through a lot of students, as well as you mentioned, through working with a lot of industry partners here.
Right. And, I always love having folks that are, independent from industry, not working for a reactor company, because I feel like I tend to get a more sort of objective take on things. Is that part of the role that you have at MIT? I know we've had Robbie Stewart on, and he's discussed the nuclear cost estimation tool, for instance. I know that you were involved in that pretty heavily. So it sounds like these kind of tools are made available by yourself and MIT in order to provide, I guess, more objective analyses of what's going on, because there's obviously lots of claims out there, lots of potential moral hazard even. So am I accurate in that kind of assessment?
Yes. At MIT, we're very much like to push open source software and open source tools, as well as open source really publication as much as possible. And one of the great things about MIT is that it does attract quite a bit of industry collaborations. And it's been through really those industry collaborations that we were able to develop tools like the cost tool, as well as some other tools that people can utilize and inform their nuclear energy portfolio.
Mm-hmm, mm-hmm. So, the reason I came across your work yet again was your update paper on the nth of a kind cost of essentially the next AP1000. That's a question that's starting to loom large, not small, as there's sort of increasing momentum, I think, towards the idea of deploying conventional Gen 3 plus large light water reactors again. This was almost unthinkable, God, I don't know, 12, 18 months ago. So the winds of change really seem to be blowing here. You've been in this world a lot longer than I have. So maybe it'd be interesting just to start with that kind of perspective that you have of, I guess, having lived through some of the earlier Renaissance, come up in that, observed some of the more recent dynamics, in terms of these years of really having no committed orders and, a lot of imagination, I guess, in terms of, turn towards SMRs and fascination with advanced nuclear, and sort of where we're at now. If you can sort of comment maybe on what you've noticed, some of the big thematic changes in the industry in the last decade or so.
Yeah, I'll be happy to. So I am a product of the original Renaissance in the early 2000s. I was recruited based on that hope, and started my work with internship at Southern Company, actually, when they were discussing having the AP1000, going through the contract for Vogel back in between 2005 and 2008. And, back then there was an understanding that we need lots of energy in the United States. That's when there were still projections that we're going to have a lot of load growth coming up. And in order to accomplish meeting that energy demand, we need large reactors, and we need lots of them. And believe it or not, actually, industry had picked the ESBWR, which is this very large boiling water reactor, over AP1000. So there were more interest in that than the AP1000. But AP1000 was a close second. And Southern was really on the leading side. And one of the things I learned, which I actually see it in some more recent projects with utilities, with SMRs, is that, when I was at Southern, it was interesting because we had some meetings about, AP1000 and how the project's going to be developed. And from some of the outsiders that are coming in as consultants, they were surprised about that. Many people in the nuclear fuels division where I interned with had no idea about, basics of the contract, or what is it that was promised, what's the timeline. And by that point, the fracking boom has happened in the US. We found natural gas cheaper than liquid water. And and at that point, once the cost of construction of these plants came to light, almost most of the players dropped. Some of them dropped after spending billions of dollars, actually. But Southern and then Savannah, which Ascana, which later on dropped, they moved forward. And what came about was that that experience was not what Southern had originally signed up for, and came up over 2 times over cost and over budget. But then you fast forward to today, where really climate change concerns have governments globally revisiting value of nuclear, and there becomes a question of do we want to continue to what we wanted to start with, which was large reactors, because now we have large demand for carbon-free energy, and for the first time actually in the US there's load growth in several markets, energy markets. There, what the utilities are doing is kind of similar to what was before, where in some cases in North America, they're rushing to, sign their contracts, getting, working with a vendor to try to deploy their project. And that, we already know from the Vogel experience, is something that you just cannot do. You cannot rush with these projects. These projects are multi-billion-dollar projects. And when this global interest started, that's when multiple companies came to my group asking basically for guidance on how do you select in this whole pool of reactors going from megawatts to thousands of megawatts. How do you go about, selecting the right project that meets their goals? And a majority of the goals is tied to cost.
Right. That sounds pretty rational.
Yeah.
Okay, I want to pick apart a few things that you said, and it's great to have this opportunity to time travel back to, I call it the naughty renaissance, because it was, the Brits talk about zero as naught, and it was the early 2000s, so the naughties. But exploring more of that, I'm curious, about why the ESBWR over the AP1000, or even over the ABWR, which had set, essentially the world record, I think, from, pouring the base mat to connection to the grid. I think 38 months in the, I'm going to butcher the name, the KK plant, Kwashiorkor Kora plant in Japan. So I'm curious very much about that. Why don't we just start there? Instead of asking long run-on questions, I'm going to maybe do some rapid fire with you. So, why ESBWR, which was another first of a kind, over ABWR, and why did we end up with AP1000?
Yeah. So the ESBWR was just like the AP1000 featured, passive safety, and back then in the early 2000s, passive safety meaning your majority of your systems can basically run with gravity. There's some other ways you can run the passive safety, but more or less, you're not relying on a diesel generator to provide source of power to run your pumps. And, that was sold to utilities and customers from an economic point of view, that now you don't need as many wires, you don't need as many pipings and pumps. And when you look at a nuclear power plant, um, some people are surprised that, typically we keep talking about concrete and steel. Well, if you look at electrical work and piping, it's a significant part of the cost. And it's a significant part of operating a nuclear power plant. It's the maintaining those and replacing those things. So from a customer point of view, it's very attractive to really reduce that burden. But then the ESBWR featured 25-30% more power than AP1000. It was a larger reactor. And so from a customer point of view, they're like, when they look at their fleet, what makes most money is their largest plant. What is most expensive is their smallest plant. So they naturally were attracted to the largest.
So that begs the question, the ESBWR, I guess, was the 9th generation from GE Hitachi, and now we're at the 10th. And the derivative of the ESBWR here is the BWRX 300. This is going completely contrary to the logic that you just mentioned that these utilities had of going small. And, you mentioned some of these, not preconditions, but these other events that are surrounding this, the Henry Hub price for natural gas, I think, went up to $15 per million BTU. I guess more expensive than water at that price. The U.S. went from beginning construction on LNG import terminals to now becoming one of the, if not the number one of the largest LNG exporters in the world. Undoubtedly, that had a major impact. I'm not sure if demand failed to materialize, but it's understandable why the industry pivoted, I think, to small modular reactors in the context of, okay, load growth maybe isn't showing up, or it's being satisfied by really cheap combined cycle natural gas turbines. But yeah, I'm again curious about this pivot to small. Like if 15 years ago, or maybe let's even in the very early 2000s, you'd told utilities, hey, you're going to save a lot of money by going small. Would they have looked at you kind of cockeyed? Or, I understand the AP 1000 came up from the AP 600. So there had been some ideas of, maybe you can build faster if you go small. But help me understand, I guess, that question. Again, 20 years ago, would people have looked at you kind of cockeyed if you'd said, hey, the secret here is to go small?
Yeah. But by the way, before I answer that, you mentioned price of natural gas, and about 2 years or so when the Russian war started, natural gas prices went up, and for the first time in a couple of decades in the U.S., we actually ended up increasing our use of coal compared to the previous year, and that's got it's a clear indicator that at the end of the day, at least for US, cost is really the key parameter that decides what energy production you're going to use. There's always talk about carbon, decarbonization and everything, but cost really rules today. Yeah. So, if you look at my own experience, so I did my PhD. Actually, was funded by a Tokyo Electric Power Company, and up until the funding ran out for some reason in 2011. About a year before I finished up. And I was all about the boiling water reactor or the better water reactor, as we used to joke about it. And in 2013, if you look at the landscape, pretty much nobody wanted to even look at a large reactor because it meant that you're betting your entire company, you're betting your entire public utility commission on it. And so, you have to look at a smaller size. And and I had done actually my master's on a compact PWR, small modular reactor, which then the Techni Atome in France picked up, and then EDF tried to commercialize as part of the New World reactor. And in 2013, I basically decided to do a big technology assessment. It was funded actually again by a private industry, looking at all kinds of technologies, all kinds of coolants, all kinds of sizes, but limiting it to a smaller size, so a company doesn't have to risk their entire balance sheet on. And I wrote this paper. Is PWR SMR or a BWR SMR better for the future? Which, as you can imagine, was a bit controversial. And they in the news they say Koroush Shirvan, the contrarian, says the boiling water reactor is a superior small modular reactor than PWR. And the arguments I used was scalability. Again, going back to cost, the boiling water reactor is already an integral form of steam generation, and PWR doesn't scale as well when you go in lower size.
Sorry, this is just for those who are less nuclear engineering than you and some of our listeners. That's just because of the need for the secondary loop.
Yeah, so you have in a PWR, you have basically a steam generator, and that goes in, and then you have the vessel, and what they had done, the SMR vendors at that point had done, almost all of them, and Westinghouse also didn't have the AP300. They had what's called an integral pressurized water reactor, similar to the NuScale reactor, similar to the leading SMR back then, which was by B&W, Empower, which was to simplify this loops because it doesn't scale well with power, by integrating the steam generator in the reactor vessel to remove a lot of the piping, so to simplify more than what the conventional loop is, so you gain back some of the lack of economy scale at lower power. But then when you look at that system still had the steam generator, which a boiling water reactor was basically the same system without it. So you can just make a very one-to-one argument that a BWR SMR would be a superior technology. So when I came out with that, I remember actually I went to GE Hitachi and asked them, so there seems to be U.S. government funding for small modular reactors. The utilities, by and large, we didn't have much growth demand back then. We didn't even think about, even power operating our fleet back in the, mid 2010s. So the utilities didn't even have much interest for new generation anyway, but there's this, climate change concerns and programs were, building up. So, it's like, this is the right time for you. And this is again back in 2013. Why don't you guys have a BWR SMR? And they told me point blank is that, listen, who's the customer? We don't believe the customer basis is real. We don't believe that demand is real. Sure, there's a lot of government program, but at the end of the day, the government program's not going to take you all the way to commercialization. So we have to have a market for it. And that was it. And then about 5 years later, that's when GE Hitachi. Well, before that, Hitachi had started post Fukushima, started working on a small boiling water reactor, and they had basically utilized the advanced boiling water reactor, which you mentioned earlier in the talk. Which was this technology that was built in 3 to 4 years, at different parts of the Japan. One of the fastest construction, nuclear construction project, the 1.35 gigawatt large reactor. And so Hitachi had kind of worked on that, miniaturizing that, which what I had proposed as well, miniaturizing from a successful build into a small reactor. But what the GE guys did in the 2018s, where became the BWX300 project, was they have mentioned that they wanted to miniaturize the ESBWR, which was the US product. And the logic was that the ESBWR, they've already have a general certification from NRC, so they don't have to spend as much money recertifying a lot of the things.
So the ABWR was certified by the NRC. Like I understand, I think South Texas project in the Naughty Renaissance. I don't know. I think there was, if I'm not misremembering, about 18 gigawatts of nuclear that got a combined construction operating license. Some of those are ABWR, so they must have been quite a ways through the NRC.
Yeah. They also had. They don't have it now. It's expired right now, but they had back in the 90s. They also had gone to NRC in the early 2000s. They had a design certification for the ABWR, which was the large reactor. Interesting enough, for the South Texas project, they did some cost analysis. And to this day, when you look at those costs, they're basically in line with what AP1000, contrast was looking at. And the South Texas was like, okay, well, this is still, the cost is a little too high. And they actually did a 20% uprate. So it was an ABWR kind of plus, because ABWR has such large margins, and if Fukushima really wouldn't have happened, the ABWR2 that was under development in Japan was actually a 25% uprated ABWR, because Japanese, even though they were building reactors, in 3 to 4 years, they still saw that the only way you can reduce costs was further power operating.
So, Koroush, something I'm really hoping you can clarify for me is, again, this idea of passive circulation. We talked about passive systems, which seem to be all the rage, not just because of safety. A lot of people, I think, have this perception that, Gen 3 Plus, are more expensive because of having to make it safer and safer and do passive safety. But passive safety actually was, A, makes the reactor safer, but B, actually saves a lot on, as you're mentioning, excessive piping, electric systems and diesel backups and things like that. But leaving that aside, what about passive circulation BWRs? Because my understanding is that, having a pump in there increases your power density. You can circulate the water better. So when did this idea of passive circulation BWRs kind of seize the imagination? And I guess that's a part of the ESBWR lineage and now the BWX300. And I want to talk about the implications of that. But first off, just to our listeners, explain the differences and maybe the logic of going to passive circulation boiling water reactors.
Yeah. So that's why when I had those designs back where I was promoting, they were all forced circulations, and I'll discuss that. So we have a passive safety as well as passively operated design. Passive safety means that when a reactor undergoes unexpected events, you are not relying on, as I mentioned, a diesel generator to provide power to your safety systems. things are naturally, you still need some batteries to open up some valves, but things, naturally, once those valves are in position, naturally able to remove um, the residual heat that exists in a nuclear reactor, um, which is one of the key hazards. Yeah,
That saves us from Fukushima, where they were dependent on these diesel backup generators that were sited too low and got flooded.
That's right, more or less. Now, a passively operating system is that during normal operation, you are not relying on pumps to circulate the coolant that removes the fission heat from the core. Interestingly, many people don't know this, but if you look at what are safety grade equipment in existing legacy plants, I'm not sure if this is true for can-do reactors, but in conventional BWR and PWR, the pumps are actually not safety grade equipment, because in all unexpected events, you always have to assume that the pump is more or less is not working. So it's not actually a safety, let's say, improvement by removing the pump. All it does is that it reduces the energy density that you can have in your core by not having a pump, because a pump allows you to pump, faster, higher velocities, higher removal heat. And so by having a lower energy density, lower power per volume, that means that you have improved your overall margin to unexpected events. So by removing the pump, you have improved your safety, but you haven't actually, improve your margin to safety, but you haven't actually changed your safety case, because these pumps are not safety grade.
I'm trying to understand the logic there, because we're stepping away from economies of scale, which I think are very well established. Like when I look at studies of learning rates, I think they're confounded by scaling, because in almost every nuclear program around the world, we have flat learning or even negative learning rates, maybe with the exception of the Koreans. In Canada, we kept costs pretty flat, other than Darlington ticking up slightly. But what we do see in those curves in terms of the overnight construction costs is a rapid drop off as we scale up, essentially an order of magnitude from, in Canada, the nuclear power demonstration project, 20 megawatts, to Douglas Point 200, to Pickering 500 in like a decade, or in the US shipping port to Zion in a decade, we go up an order of magnitude. Yeah. Prices drop dramatically. So we're turning our back on economies of scale, and then we're moving towards a reactor concept which has a lower power density. We'll get into the civil works side of this, but it seems like we're going in an interesting direction here. Can you talk as well about, because we're going to, I think, deep dive the leading SMR at this moment globally, the most advanced one in terms of the one in my backyard, passive circulation, what that means just for the kind of geometry and architecture of the plant. My understanding is with the aircraft impact assessment rule, having a really tall plant complicates things. So what with passive circulation, how does that change the architecture of the plant and the reactor pressure vessel?
So again, the passive circulation, again, not needed from a safety point of view, makes things larger. Now, why do anyone would ever do this? In fact, every reactor operating, whether it's on the sea or the land right now, is using forced circulation pump. It's whether it's military or civilian, we're using force. So why would suddenly these U.S. only companies? So if again you go overseas, you go look at the Chinese SMR, the CNP 100 that's being built right now, forced circulation. Rolls-Royce, all these things are forced circulation. So why is it that only few U.S. companies decided to do this? If you look at the 1990s, nuclear was dead from a point of view of policy. Both parties weren't really that excited. The Democrats back then were in charge in the Clinton era, and it really had no hope in terms of having a future. And the fully passive safety was really born out of that anti-nuclear era as a way to address public perception. It wasn't to address any type of, let's say, engineering novelty or engineering improvement or evolution. It was mainly to address that specific US negativity about it. So what's the implication of that to design? So there's two sides of this. So one is that it makes the system larger. The civil works become large. The equipments become large. So cost will go up. There's no...
What causes the civil works to increase? Making passive...
The passive operation, yeah.
We're talking circulation or passive safety systems right now? We're talking passive circulation?
We're talking about circulation. Yeah. Circulation, passive circulation will make everything bigger. In a boiling water reactor specifically, it's very harmful. One is that in a boiling water reactor, you have your control blades that control the fission reaction. They come from the bottom. And, if you're gonna, these are real systems, okay? These are not cartoons. So you have to maintain them at some point. So you have to take them out. In order to have enough space to take them out, that means you got to bring up the reactor by however you increase the size of the reactor. Then you need a large space between the core and the top, which is called the chimney region. You need a large space there in order to actually promote this circulation. And in a BWR, you're also your water level is also dictates how you're gonna refuel. So you're gonna bring the assemblies right there, and so that lineup also gonna change. So the core length, as well as the overall vessel height, will also impact the containment size. So it's a very much correlated to a lot of things. And so if you have a low power density and a tall core, your system can be very large, so you better be pumping out a lot of power from that large system. The second thing is your passive safety. How do you design that? In the AP1000, which features the most compact, by footprint, by a lot of metrics, materials use per energy produced out of other technologies. They decided that they're going to have these passive safeties systems good enough for 72 hours without operator action. Some of these vendors are now targeting 2 weeks, a month, indefinite. And so when you go to that level, then you need very large tanks of water or cooling or very large systems to lower the power density even more to be able to remove this residual heat that, once you shut down the fission reaction, you have all these residual heat, we call it decay heat, that you have to remove. So that's another thing which becomes a misuse of, passive safety, where you're trying to go for, unbelievable rates of, quote unquote coping time.
Right. All right. So again, my understanding here, trying to summarize what you've just said, by going to a passive circulation system, I guess on PWRs or BWRs, you drop your power density. We're going against that historic trend, and logic that has driven the industry and driven the cost reductions, which is economies of scale. And we're making a less power dense reactor, which means that the civil works, to accommodate a much larger vessel and access from the bottom, access from the top, mean proportionally our civil works are going to be a greater component. But yeah, can you just describe that for the BWRX 300? And is that why, I'm not sure if there is a history of other commercial grid scale reactors being underground in the way that the BWRX is, but that seems to be one of the ways they accommodate this really tall reactor building and reactor pressure vessel, while also trying to stay under the skyline and probably minimize some of the construction required to address the aircraft impact assessment rule?
Yeah. So as we talked about, the original idea behind BWX 300 was to be a derivative from ESBWR. But, if you take something like ESBWR and you reduce the power rating by a factor of 5, you're talking about a massive cost increase, right? So what the designers initially did was to remove a lot of the safety systems that existed in the ESBWR in order to combat this lack of economy of scale. And by removing the safety systems, they could then make the containment or the building structure that surrounds the reactor vessel compact. And then maybe you can, excavate the ground more easily for this system to be there. So that was the original concept. So what happens then? You go through the regulatory process. You find out that because the other key part is that US AP1000 was designed in the early 90s. ESBWR is similar to ABWR. There has been no design activity going on really for over a decade. So people who were designing reactors are retired more or less. I had for my thesis that was on high power density boiling water reactors, I had it reviewed by folks that designed the original ABWR and ESBWR, and they were already retired at that point in the early 2000s. So now you have people who don't have design experience designing this thing, and they go to a regulator, and the regulator says, listen, these pipings that you have, you have now, narrowed down, leaned your system to one set of safety systems. Those pipings you have to assume they're gonna crack. You have to assume they're gonna leak. It's just not gonna, you're not gonna be able to argue that somehow you have, a better connection, you have a more advanced connection. Now we're gonna give you an exemption for this. And so what happens is that, okay, so now we have to add safety systems. They wanted a dry containment, all BWRs as well as PWR SMRs, they have wet containments. A wet containment means that you have pool of water in there to absorb the heat so you can make things compact. And now that they have to add safety systems, they had to choose, do we go back to the ESBWR way, or do we try to, on the fly, come up with a system that would address a regulatory concern? It seems, based on what you see out there in terms of design documents, they basically made a reactionary feedback based on the regulator demand that now I'm going to have to add this system. I'm going to have to add this system. And so now what has happened is that narrow structure that you could have buried underground has become wide enough to the exact same size as the ABWR reactor building at 1350 megawatt. And so now that becomes, of course, a much more complex excavation for a 300 megawatt electric plant versus a 1350 megawatt electric.
My understanding is that, again, this initial design with a very, compact, narrow core, and we'll throw an image up right now comparing the two, or the design evolution, I guess, from, I think, 2019 to 2023. But that's, that shaft looks like it's got an obesity problem. I think the reactor building volume goes up 300% from, a diameter of, correct me if I'm wrong here, but 20 odd meters. I think we're up to 36 meters in diameter. I'm trying to think of something I can quickly compare that to in terms of, frequently encountered building size, but quite a big diameter there, 90 feet. My understanding is that the original concept, thinking about constructability was, hey, we can use a vertical boring machine to quickly excavate the shaft. And if you have to go through strata that aren't just kind of loose sedimentary, but have to actually go through bedrock, that was a argument to sort of speed up something, which I think is not commonly done. And maybe if you can just clarify that earlier question, have we buried grid scale reactors before successfully? Has that been something we've done commonly?
For a lot of large reactors, like you take EPR for example, it has, it's because of its numerous active safety systems. It's a very large reactor, over 1600 megawatt electric. you know the base mat needs to be, you need to like excavate like 40 meters for just to put the base mat. Depends on all these things, depends on geology and soil. So I don't think the physical depth that you're excavating, let's say it's way outside of the current experience base. But then at the end of the day, that EPR or the ESBWR, you're getting more than 1,300 megawatt electric out of it, versus here you're doing comparable things at 300 megawatt electric. So that's to me is the main economic implication, rather than, let's say, outside of the bounds of nuclear industry.
Right. In terms of that excavation, I was reading through some of the construction documents, and they were saying, if they hit bedrock, they've probably got a jackhammer, use, I think, what was called like pavement breakers. Can you like blast if you are into bedrock? Like it sounds like it's very site specific. If you have some nice sedimentary geology, it's nice and soft, this will be an easy excavation ish. With bedrock, is that a concern?
So the typical thing you do is blasting, and blasting has some implication in terms of, if you're gonna like build like 8 of these. Now in Ontario Power Generation, they mentioned they want to do 4. They want to do 1 first, and then three later, which is smart. You do blasting. You can, of course, do a lot of other activities. But what fundamentally this becomes is that every site has to come up with some kind of a specific design. So in America, we have utility like Tennessee Valley Authority interested in this. Well, they can't take that design and build it here. It's very different geology, and this design is very much from a point of view of seismic coupling of equipment to structure and soil. It's all very much coupled together. So they have to do a lot of changes here. So you're not going to have this standard design that you're going to be able to like build as is everywhere, which is, you mentioned, nuclear realizes negative learning to that. I think if you look at the data specifically, you're going to find learning, but for that, there's several requirements. Has to be the same site, has to be the same constructor, has to be at least 2 years of gap between one construction to the next, have to be constant labor laws, have to be constant regulatory. And when you add these 5, you only get like 4 or 5 examples in the world. And you, from those examples, then you can see learning. So it's gonna basically be a challenge in terms of standardization.
Right. So just getting back to that idea of the vertical boring machine, is that a game changer? Would that have made things easier? I was looking up tunnel boring machines. The largest in the world is, I think, 23 meters. China, heavy industry and railroads. Is it the same thing as a tunnel boring machine?
Well, for this design, they're not going to be able to do that, because that's this design is too large for the world's best boring machine. Overall, the idea is that it does bring a bit more certainty. Not much, let's say, cost advantage, because excavation believe it or not, is not actually big. There's still there's a whole cost of equipment and all that stuff that needs to be done, and then there's operation and maintenance. So when you look at the overall cost of energy generation from a plant, it's a minor part of it. So it's not like it's a game changing technology.
Okay. Again, out of curiosity, I'm just trying to think things through and probably going into more detail than I need to. But Darlington, there's an active nuclear station there. Can you blast? I think the SMR site is under a kilometer from 4 large CANDUs, or would that trigger some sort of seismic detection that would scram the big CANDUs on the other side of the site?
Yeah. I was there actually a couple of months ago. Yeah, there's you can see kind of this site is over there, and the Darlington is there. Yeah, I'm not sure what if construction activity gonna impact Darlington. So
Okay,
I can't really comment on that.
That would be speculative. Okay, so you're saying like excavation is pretty uniform. You got to go down deep. Huge reactors, you also have to go down deep because you need to seismically isolate these systems. But again, in terms of burying the RPV, the reactor pressure vessel, does that matter? Would it be like a less complex design if the BWX 300 didn't have to embed the vessel and just had it going up vertically from grade?
But then you run into wind and missiles and aircraft impact, which we in the US we take it seriously. As I mentioned earlier, like BWRs, you try to have the spent fuel pool to be in line with the water level of the reactor, so you don't want the spent fuel pool to be way up up in the air either. So yeah, there's a lot of things, but as I mentioned earlier, in a BWR, when you add pumps, you remove this chimney area, and then if you're having a small power outlet, you have to come up with a shorter length core proportionally to what you're doing, and then that's gonna really shorten the reactor, because for every meter you save in the core, there's 5 meters overall that you save elsewhere. So that's why unfortunately what I've seen is that vendors aren't designing for, let's say, costs. They're designing either to lower the licensing burden or try to let's say simplify things, but then the licensing burden comes in to get them. Yeah, it's not really a very good iterative process that they have now.
So, I mean, as like an armchair enthusiast with the benefit of a retrospectoscope, it does seem like there are some sort of, I mean, they're probably big conceptual errors. They start as small little elements of a design process and then can blossom into something that's a real problem. And I think NuScale is a big example of that, where the module itself is incredible, right? This integrated reactor pressure vessel and steam generator. This idea of like, let's build airplanes, not airports. Sounds like a great idea, right? And let's get them done in factories. But then they forgot about the airport. The world's largest swimming pool, I understand it's kind of rectangular, which seismically requires like a lot more overbuild of just the thickness of your walls, and has to pass the aircraft impact assessment rule. And then you have this, the power modules are an awesome thing, but conceptually you've forgotten about the airport. And maybe with the X300, there's something kind of similar going on there in terms of passive circulation versus having pumps in there, which would have reduced civil costs, which, correct me if I'm wrong, but are far more significant cost driver than just the nuclear steam supply system.
Yeah. It's almost equal, between the because equipment, there's a time consuming part of installation. So if you account for installation and equipment, it's actually a bit more than civil. The like NuScale, you look at it and they've been, to me, NuScale has been an extremely positive thing for the nuclear industry, because they argued and God really blessed them, and they spent over $1 billion on this design, and they asked for a lot of exemptions from NRC. They battled with the Nuclear Regulatory Commission in the US. They're still in the world the only approved methodology to reduce emergency planning zone. In the world, the only approved methodology to use one set of digital INC control room to operate multiple reactors, which are, things that you do, in other businesses, but in the nuclear regime, we're always tend to be a little bit behind times and more conservative. And so you look at all those battles they won, and you would think that others would leverage those battles. Sure, their design, again, is a fully passive operation, as we discussed, very large, so it becomes, very big per energy produced. But you will look at those battles that they won, and unfortunately, when you look at like the X300 and other SMRs, they're not actually talking about shared control rooms. They're not talking about shared auxiliaries, and those are the ways that you can realize additional cost savings. And even there, these systems aren't leveraging their full potential, unfortunately.
Hmm. Well, maybe let's shift gears a little bit from a lot of this kind of design specific locker room chat, water cooler chat, whatever the analogy I'm trying to erroneously make is, to some of the modeling work that you've done again on trying to cost things. I had the pleasure of having Jigar Shah on last week. We were talking about the DOE liftoff report. And again, really a paradigmatic shift there, I think, from the liftoff report just 1 year ago. A clear acknowledgement of diseconomies of scale, of the need for a quote unquote burn-in period for Gen 4 technologies to get through a lot of the, operational capacity factor related problems that these reactors have had in the past, and get, to the state of commercial readiness. But yeah, I mean, comparisons of large and small. I pressed Command F on the both documents, and in the previous liftoff, AP1000 appears once. In the current document, it's there 44 times, over 40 times. So there's been a big shift, and coupling that with the TVA integrated resource plan, pretty just freaky numbers there. For both small and large, but certainly a big difference in terms of, I think representative of those economies of scale on a per megawatt installed and a per megawatt hour basis. So maybe walk us through some of the math on that, where things are kind of looking in terms of, the most economic way to reach climate goals, to, reach, the massive power demand from AI data centers. Not to go on too long of a rant, but one of the questions I posed to Jigar was like, if we were back in the early 2000s, in the noughties, before the fracking revolution, nuclear was a matter of national security, of energy independence policy. It wasn't a nice to have technology as it is kind of now to fight climate change. It was, I think, very much a need to have, and that led to a lot of the sort of pragmatic drives to push it forward, to make the investments, to get those COLs in place, those combined construction operating licenses. There was a real seriousness. And if we had that same kind of urgency, whether it was economic or national security, one would think that you would really focus on, okay, what's the lowest cost pathway to quickly add, as many nuclear gigawatts as possible.
Yeah. So as I've detailed in various reports and various publications, if you're looking at the the lowest cost, of course, a large reactor way is the would be the answer. With both large and SMR, you have two learnings. You have the first of a kind learning, and then you have the standardization learning to get to nth of a kind. As I mentioned, to get to realize learning, you need like 5 key things for it to happen. And naturally, as I've been telling in a lot of my recent presentation, in nuclear, whether it's a SMR or large reactor, we can never have million reactors in order to realize the same absolute learning as solar PV panel. So we have to deal with technologies that have low cost of equipment, low cost of civil structure per energy generated, and because you're not at the luxury of deploying thousands of these, you are basically limited by economy of scale. The other point that it's written in my reports that maybe not as appreciated in other things, including even the liftoff report, is that when you look at the lifetime energy cost of a nuclear power plant, half of it is O&M and fuel. It's not 20%, 10%, 30% that people come around. The capital cost, you have a 20-year financing period, and this is where the large reactor have their issue. That's why we're not building large reactors right now actively in the US is it's an enormous amount of capital that you have to finance. But then, 20 years, 30 years, once that paid off, these systems with minimum amount of refurbishment in the LWR world and more substantial refurbishment in the can-do world, they can operate. The structures are good enough to operate to 60 to 80 years. Now, 80 years, we've already gotten licensed to 80 years. And 100 years seems to be, possible. And because of that, you're actually paying half of it over the lifetime is actually O&M and fuel. And when you look at O&M and fuel, number of components matter. Are you using a low-enriched uranium that has a good, supply chain, things like that? Those things matter, and that suddenly again pushes you back to the world of water-cooled reactors at a large scale, because for let's say I take AP 1000 versus AP 300, you've reduced number of components by 10%, 20%. You haven't reduced the number of components. So when you divide the refurbishment and maintenance of those components per energy generated, you immediately see that gonna be much larger. So that's same thing for number of operators and security and all that. So that's another important thing that basically brings you in. And when I use those realistic, very conservative learning rates on these large projects and look at regions, Southeast Ontario, Ontario's grid, or the Northeast grid, you see that actually, the nth of a kind for the large reactors, you can actually get to a point where you're very close to the current electricity generation prices. And that's really the key, because when you try to decarbonize, every other model shows right now that the generation costs will have to, increase substantially. And that's one of the key things. Now, with small modular reactors, when I look at it, unless the vendors are willing to share auxiliaries, share control rooms, do a lot of things that maybe one vendor does, but not the other does. If you combine all the attributes and do even more, then I still see that they're a better, on the nth of a kind, they're a better technology than when you look at solar or wind plus battery storage plus some natural gas as the ultimate backup to have a base load or a dispatchable source of energy, at least today. But without those, the cost argument becomes very challenging to make.
This is completely fascinating to me because, I think it was just sort of a standard engineering and finance assumption that, okay, we're going to, assume the life of the plant is 40 years and hence amortize costs over that time period. And so we hear this very frequent, and I'm just reiterating what you're saying here, but I just want to, because I think it's really a powerful takeaway for me. Typically, we're told, the OEM of nuclear, the OPEX of nuclear operational expenses are very low because you have very cheap fuel. You have labor, which is expensive, but it's not like buying natural gas or oil or coal as a big driver of cost. Majority of the cost is in the capital cost. But when you operate this plant for 80, maybe 100 years, the operations and maintenance, that OPEX becomes 50%. That is kind of brand new to me. So thank you for sharing that, and apologies to the audience if that was already obvious to you. So let's talk about some numbers. The TVA, IRP, just to give something a little less abstract, is saying that the first of a kind light water SMR, presumably the BWX 300, because that's the project that they're quite involved with, close to 18,000 US dollars per kilowatt for the first of a kind unit, and then getting down to something around 12,000 US dollars per installed kilowatt. So a lot of learning there is something that jumps out at me. that very high first of a kind cost is hard to ignore. We're building one of these units up in Ontario. And the whole premise in Ontario, I think, is that, we'll be a leader on this exciting new paradigm of small modular reactors. And then we'll be able to have a big chunk of the kind of export markets domestically and internationally. My concern is that export market may fizzle as the SMR paradigm starts to fizzle, as countries become more serious about deploying, and utilities really look at the economics. And I just, my spidey senses and the DOE liftoff report and some other, facts seem to be pointing towards that happening. I mean, Poland, they're still, Orla Synthos still talking about SMRs, but mostly it's the private developers. Polish government, they want big AP1000s or Korean APR 1400s. So that's kind of my concern with the sticker shock of the first of a kind cost. But tell us, why you think that cost is so high, and why the learning rate seems to be so good there in terms of getting down to nth of a kind, specifically the TVA integrated resource plan, and that $18,000 down to $12,000 per installed kilowatt.
Yeah, so those numbers are actually in line with what I put in my latest report as an independent calculation. So since they're aligned now, will the breakdown of the cost that I have, is that going to be aligned in TVA? I'm not going to make that a speculation, but let's say if it is, then what are the drivers? So as we talked about, the plant is as big as a large reactor, but generating fourth of the power. But one of the things that's not talked about is owner's cost. You have and TVA, is looking at the Clinch River site, which they've already spent over $100 million to get a license, license for.
Specifically for the BWX, or just is a nuclear site?
Yeah, the BWX is in their environmental plan, but you can use that site for really any nuclear power plant. So those costs, again, it could have been for a 1,000 megawatt plant, 300, 4 of these. That's a fixed cost. Over $100 million you pay to get a pre-license, and then you got to bring in utilities. You have water, electricity, gas to support the construction. You got to have a security detail. You got to pay all these fixed permitting costs. And when you add those up, an owner's cost becomes very, very hard to change, whether it's for one SMR, two SMR, 2 large reactors. It's very much almost the same cost. And so when you look at that cost, that is for one unit in a greenfield. And that a big chunk of that is actually this owner's cost that does not show up to any type of vendor discussion or any type of cost that gets thrown around. And typically then people go and use owner's cost, so we add 10% to it. It's actually close to 30 to 45%. According to my estimates, close to 40 to 45% of the total cost. Yeah. And so once you go to you build a lot of these, that owner's cost gets divided towards them. And that's why you see a lot of that learning actually comes from just that.
I'm not sure if you had access or know the underlying assumptions to the TVA numbers, but to get from that 18,000 essentially to the 12,000, it sounds like you're diluting that owner's cost between a number of units. Are they talking 4 units, 8 units, 100 units? What are we talking?
I can't share those data.
Okay.
Yeah.
Okay, fair enough. We'll assume it's a number of units anyway.
Multiple units.
Yeah. I mean, the first of a kind cost on the TVA IRP is I think around 12,000. So it's the nth of a kind cost for presumably the BWX 300. And the liftoff report, and I think your own work on next of a kind AP1000. Why is 12,000 is still pretty high. I think Vogel in inflation adjusted dollars ends up being about 15,000 per kilowatt. So this is an improvement, 12,000, but it's still high, particularly when comparing to the Chinese. Why is it still so high, and how much room is there to maneuver and get towards if we're looking for a Chinese rate of deployment, the DOE's goals of 200 gigs additional by 2050, that's 13 gigs a year. We need to get down to those sort of, as close as we can to those sort of Chinese costs. Run on question here, but tell me about the TVA's estimate and where you think we can get in terms of.
First, the Chinese are building a single unit SMR, and they've mentioned in their reports publicly that they believe that it's going to be at least twice more expensive per kilowatt than their large reactor. They have put a 58 months schedule. They spent 2 years completing the design before constructing it. Everything is out there. I don't think, and my models and estimates are in line with what the Chinese are talking about. So there's no, let's say, a secret into this.
There's not like one country that's deploying SMRs and it's way cheaper than large. The industry's just hyped this. Yeah. They've hyped it so much. Anyway, carry on.
This is where, why I decided to publish that latest report by trying to put what I think are realistic numbers to but at the same time, you got to normalize things, right? When you look at other sectors, solar, wind, natural gas with carbon capture, they're doing the same thing. And if we don't do it on our side, in the nuclear side, we're going to fall behind. So you have to have an optimistic look if you're in a particular industry. Otherwise, you're going to fall behind because others are making the similar promises. But as I mentioned with the with TVA's nth of a kind cost, again, they're pretty high and they're nowhere close to the Chinese, giving labor and everything else. But if you normalize all that, is mainly because the vendor has not told them that we're willing to share control rooms. We're willing to share auxiliaries. We're willing to share, turbine halls. And so when you're building this large one again and again, you're not going to see, great cost reduction. So when I, make those assumptions on that, let's say we share these things to lower the cost. And again, as I mentioned, some SMRs do one of these things, not all the things to reduce it. I see it that it goes down to $6,000 per kilowatt, still higher than the nth of a kind, a large reactor. But
this is what we're talking, like the AP1000 numbers is 6,000 per kilowatt.
No, the SMR, if you do a lot of share. Now AP1000 again, the getting close to like $5,000 or so. Dollars per kilo. So still, SMR is always going to be higher no matter what you do. But I believe you can actually decrease these costs if you do a lot of different design approaches
and best practices, essentially.
Yeah.
I guess maybe a closing question. We've been talking for just over an hour now. How is it that there's been sort of, what one might charitably call sort of design errors or sort of conceptual errors or failure to incorporate, all the best practices? How do we get around that? I mean, I would assume like an institution like MIT, that would be part of the mission is, okay, like let's not allow these small, again, conceptual ideas that maybe led us a little astray to do this again. Like, obviously these are all vendors that are competing with one another, and there's all different kinds of personalities involved in the engineering divisions and the reactor designers. But yeah, how do we ensure that we have, and we learn and we apply all these sort of best practices?
I think we can, keep talking about it. We've had I feel like there's a best practice report getting rolled out every couple of years. At the end of the day, every industry is able to actually use best practices if it's healthy. Right now, in order for us to have a chance, we have to use a lot of government support, whether it's US or Canada. Let's face it. And that means that we are an industry that is on life support, and our life support is from the government. And that becomes hard to do the right thing every time. Because if we were an extremely profitable industry from point of view of new generation, then those profits could go back into actually implementing these lessons learned. Versus government funding always comes with some kind of a prescriptive, which is one of the key issues. And I think this is what really led to the SMR program in Canada, is that again government said, hey, you gotta go deploy a small reactor. You gotta have modular construction with these things. Like, why should the government even dictate a technology or go down to the level of details of how you're going to construct this? Just here's money. Go, you go and go deploy the best thing there is for your, for your company. And unfortunately, that's not how it works when you're dealing with government. And that's really what's happened. Like, if instead of paying all these like 10 different companies in the US like billions of dollars trying to license, develop, mature their technology so they can like license it, and the government then pays their licensing fee. That's great. But then when it comes to detail engineering, it's like, well, it's up to you now to pay for that. Well, that's what makes the difference between 2 times cost overrun and 20% cost overrun. And unfortunately, this is where we are, where government is a life support. Government is not making the right the right programs that would give the nuclear industry the best shot, and we're not able to actually execute on these best practices. But because otherwise, a lot of agency, Nuclear Energy Institute, there's a lot of consulting companies like NPR in the US, and there's similar things in Canada. It's we know what to do. Is just how to implement it requires the right structure of support.
Right. Yeah, I mean, it's interesting. In Illinois, Governor Pritzker's lifting of the ban, but only up to 300 megawatts. That's a perfect example of government dictates that aren't necessarily logical. In some way, I think the industries impose this on themselves by embracing the SMR paradigm, I guess, as a way to sort of stay on life support and survive. In Canada, my organization was very involved in removing the SMR only language from things like our investment tax credit.
Congratulations.
Yeah. I mean, I think, again, need that freedom to go after best practices in industry that's struggling. Koroush, thank you so much. You've been very generous with your time. Very, very important insights that I personally gleaned from this, and I'm sure our listenership feels the same way. I really look forward to having you back on. Thank you again.
Yeah, thank you very much, Chris. Enjoyed our talk.